Hello. Hello. Hello and welcome to this week's string seminar. Today we are very happy to have Suneeta from ISO Pune, and she will tell us about the generalized second law in cross-product constructions.
So thank you very much for the invitation to visit here. It's a really nice place. So I'm going to talk about the generalized second law. And I'm going to explain the generalized second law and also cross-product constructions. Okay, so generalized entropy was actually introduced by Bekenstein in order that the second law of thermodynamics be valid near black holes. Because you can have stuff going into a black hole and the thermodynamic entropy of the outside decreases, violating the second law, or you could have radiation coming from the black hole. So what he conjectured was that this object, which he called the generalized entropy, is always never decreasing. So this is a combination, this is a combination of the area of the black hole and something which he called S out, which he, when he proposed, took to be the ordinary thermodynamic entropy of matter outside the horizon. And the GSL is the statement that this entropy never decreases. Now you can ask what happens if you have quantum fields outside the horizon, for example, when you have Hawking radiation, what should we take S out to be? And Sorkin pointed out that it should be the entanglement entropy minus trace rho log rho, where rho is the reduced density matrix of the black hole exterior. However, this object has a well-known UV divergence. Now there is a lot of evidence for the idea that in this combination S-gen, the divergence in the renormalization of G here exactly cancels the divergence in the entanglement entropy, and therefore this combined object is finite. So the generalized second law has actually been proven by Wall. This was proven for Einstein gravity under the assumption of some kind of a renormalization scheme that renders some quantities such as this entanglement entropy or something called the boost energy, which I'll show later. It renders them finite. So he assumed this renormalization scheme, and with that he proved the GSL. So what I want to talk about now is one such renormalization scheme, an explicit realization of a renormalization scheme, which makes all these quantities finite. And this was by Witten and later by Chandrasekharan, Pennington and Witten. And these people describe the entropy of an algebra. So this is a statistical entropy which is associated with the algebra. And the algebra in question is the algebra of observables in the exterior of the black hole. So what they showed was that the generalized entropy of the Kruskal extension of the Schwarzschild black hole at its bifurcation surface is precisely the entropy of the algebra modulo a constant. So generalized entropy is algebra entropy. That's what they found. So they also tried to use properties of this algebra entropy. So they had a monotonicity result for this algebra entropy. They tried to use that to prove the GSL. So what they did was they proved a version of the GSL using techniques from von Neumann algebras. Specifically, they said that the generalized entropy increases from early to late times, okay? Provided there is a large time gap between the early and the late times, and the black hole is allowed to equilibrate between these two times. So there is nothing falling into the black hole at these intermediate times. And then they were able to prove a version of the GSL for asymptotically ADS black holes. So this is not quite a local GSL, which would be the statement that if you compute the generalized entropy at any cut of the black hole horizon, then as you increase the cut, it is non-decreasing.
So the monotonicity they couldn't show.
So monotonicity, no, they had a monotonicity result for the algebra entropy. So the algebra entropy is a statistical quantity associated with algebra of the exterior of the black hole. And what they were able to say was that if you have a subalgebra they were able to compare the entropy of a subalgebra with the entropy of the algebra and get some kind of a monotonicity result. And they used that result to prove even this version of the GSL.
But this one is just comparison.
This is comparison between early and late times. That's it. Yeah.
And why does Einstein gravity enter into this?
So so the calculation is explicitly for Einstein gravity, where S gen is area by 4G plus the entanglement entropy. But in a paper last year, we showed that it's also true for any higher curvature theory of gravity. You just replace the walled entropy instead of the area, and then it's true. The same, I mean, the whole, whatever they did can just be done.
I understand they don't really get the entropy, right? It's what we say modular constant. They really get the change of entropy between.
Yes, that's correct. It's only defined up to a constant.
I mean, the constant is probably a big constant.
Yes, it is a big constant. Yeah. Yeah. So it is a big constant in the limit that G goes to 0, which is what we are studying.
Constant in the sense of constant.
It's a state independent constant. Yeah, it's a state independent constant.
It's like saying if you have a black hole and you perturb it, how much does the entropy change? And the way you get the Einstein gravity is you use the first law of entanglement of that, which will tell you that so it's like these earlier work on entanglement. So then you try and show the change in the modular Hamiltonian is related to the stress tensor, and that's how you get these.
So you also have to use the semi-classical version of the Raychaudhuri equation, and from there you get the difference of areas at 2 times. So the Raychaudhuri equation explicitly uses the equation, Okay, so they didn't quite get a local GSL, but whatever has been done, as I just said, can be done for an arbitrary diffeomorphism invariant theory of gravity. Okay, so this is just a picture which I can probably skip since it's clear what the early and late times mean here. So there is a large time gap between the early and late times where nothing falls into the black hole. So what these people did was they employed an algebraic procedure called the cross product to render the divergent quantities finite. However, you still don't have a local GSL. So what we will show in this talk, is that it is possible to prove a local GSL in cross product constructions with no assumption on the matter falling across the horizon at different times, and this also works for asymptotically flat black holes like Schwarzschild and Kerr. Okay, so let's just go to the basics, which I'm sure is elementary to a lot of people here, but I don't know who else is joining in Zoom, so I thought I will give an outline. So here is your Schwarzschild black hole. So we are going to deal with Kerr also later, but for illustration purposes, I will have a Schwarzschild black hole. So here's a Schwarzschild black hole with a Cauchy slice in red, and you can see the right and the left exterior. So what we consider is the algebra of bounded smeared quantum field operators, which are either in the right or the left exterior. We consider both these algebras. So, let's just quickly go into von Neumann algebras, which we are going to use here. So, if you have an algebra S, which is generated by a subset of bounded operators on the Hilbert space, and if you include the adjoints of all those operators also in S, then this is a star algebra. And we define the commutant of an algebra to be the set of all bounded operators which commute with every element of S. And von Neumann algebra is a star algebra that equals, sure.
Can you be a little bit more explicit? I mean, if you...
About the...
you drew that diagram, the Penrose diagram. There's a Cauchy.
So let's go back to the diagram.
So what are these operators? You have in mind,
so let me just write it.
What is bounded?
So you first start with your field operators.
Yes.
And then you take a smearing function. Let us say I'm interested, so this is my whole, say Schwarzschild black hole. And I consider some region. Maybe I consider the whole right exterior, okay? So I take functions, so I take the field operators, and then I multiply that by smearing functions, which have compact support inside this region, and then I integrate. So this gives me a smeared field operator, which may still not be bounded. So what I do is I have to consider bounded functions of these smeared operators. Yeah, so let me just explain to you why we need boundedness. So I define the norm of an operator, okay, to be the supremum over all state psi in a Hilbert space of O psi norm, where this is the Hilbert space norm, by the norm of psi. Okay. Now the problem is, if I took this operator to be just the field operator localized at some point, and then if I try to compute this norm would be infinite because of the divergence in the 2-point function. So this norm would basically be the root of phi x prime expectation value in the limit that x and x prime are approaching each other. So this would be divergent. So that's why we cannot use field operators. We have to use smeared field operators. Not only that, you have to use bounded functions of smeared field operators. So if you don't have bounded operators in your algebra, then you even something simple like composing two operators. Okay, so suppose I take some phi 1 and I phi 2, and I act on some state in the Hilbert space. If this one is of infinite norm for some states, and this one is of infinite norm for, this one is infinite when acting on some states, and this one is infinite when acting on some other states, then we will have a problem.
So this psi that we are talking about
is a state in the Hilbert space. So the Hilbert space which I will be interested in is the Hilbert space of quantum fields. So that is in the right exterior of the black. Okay, so yeah. So actually the algebra of the quantum fields in the right exterior is a von Neumann algebra. So let me just define what is a von Neumann algebra. It's a star algebra that equals its double commutant. Or in other words, you could say that you take operators in the algebra and take the limits of operators to also lie in the same algebra. You include them, and then you form this von Neumann algebra. So the algebra of quantum fields in the right exterior is the von Neumann algebra, and one can easily deduce its commutant because you just look at the largest space-like separated region from the right exterior, and that's the left exterior of the black hole. So the commutant of this algebra is the left exterior, algebra of fields in the left exterior. So the algebra, the algebra of the fields in the right exterior is actually something called a type 3 von Neumann algebra in this classification of von Neumann algebras. So I will just briefly say what are the properties which distinguish the various types. So type 1 and type 2 von Neumann algebras have renormalizable density operators. So I'm going to explain what is renormalizable. So the idea is once you have a density operator, you can do minus trace rho log rho, and you can define some entropy for the algebra, which is a statistical quantity associated with algebra. So you can consider you can consider the von Neumann entropy associated with the density operator. Now type 3 von Neumann algebras have no renormalizable density operators, and what I mean by renormalization is basically by defining a modified trace, okay, on the Hilbert space in situations where the usual Hilbert space trace is infinite. So I will go into details about what this trace looks like in a while. So in order to define the entropy for the algebra, it must be type 1 or type 2, because if it's type 3, you do not have density operators. But the point is that the algebra of quantum fields in the right or the left exterior is a type 3 algebra. In fact, quantum field theory operators, the algebra of quantum field theory operators in any proper subregion of your space-time is a type 3 algebra. So you don't have density operators. But there is a mathematical construction which you can do, which is called the cross product by the modular automorphism group. So I'm going to explain all these things. Now this is a way of extending the original type 3 algebra so that it becomes type 2. And once it is type 2, you have those nice density operators, and then you can define an entropy for the algebra. So that's exactly what I said here. Okay. So what is the cross product construction? Let's go over it. So what we do is we have a type 3 algebra of quantum fields in the right exterior. We enlarge the algebra by adding one operator. And we enlarge the Hilbert space to also get states on which this extra operator acts. So Witten's idea is that what you do is you consider a low energy effective field theory of quantum gravity. So you can have matter, you can have gravitons. But if you just think of gravitons as one more field in the system, then the algebra of fields is just type 3. And we are interested in this theory in the G going to 0 limit, when we have the space-time picture clear. So we want perturbations in geometric quantities to be small.
So you don't have to add the operator, it's already there.
No, you have to add it to the quantum field theory operators. So it's the ADM mass, right, which you add, which is.
If you have any finite, if you take into account the first G Newton correction, this operator is already there.
Yes, I agree with you. If you take the first G Newton correction, the operator is there, but it's not there in the limit where you just have gravitons propagating in a Schwarzschild background.
There's no dynamics.
Yes.
That's not closely coupled with that.
Yes, that's exactly. At the first G level, it is there. I agree with you.
Can I just see the previous?
Sure.
So you have, so the statement is that the algebra of fields in this is type 3 because of what you said. But you want to now do a construction
Which is going to make it type 2.
type 2, but for that you will be coupling to gravity?
No, you already have gravity as gravitons on a background. You're going to go to the next order. So what he's saying is absolutely the point that once you go to the next order beyond the linearized order, you have the natural operator. Yes, but yeah, exactly, you are doing that. And in a sense, they are doing it by hand. Instead of saying that they are going to go to the next order, they are just adding one more operator, which is going to be the ADM mass.
I think it's I mean, my understanding of the picture is that when G goes to 0 in this limit, which is not really gravity, it's really quantum field.
Exactly.
It's type 3. In the perturbative limit, when you consider perturbative corrections, it's type 2. Of course, if you consider.
When you go to, yes, sure. When you go to second order perturbations, it's type 2.
Yeah, so, or leading non-trivial.
Yes, leading leading beyond the linearized order.
Just the ADM Hamilton appears immediately. I know, the linearized order is not, I'm not calling that.
Yeah, it's a next order.
The first non-trivial.
Yes.
And if you include all gravitational corrections, it's type 1.
It has to be type 1, yeah.
I mean, in ADS it's clear, right? It would be the algebra of
All the entire CFT, yeah.
But in perturbation theory, the claim is type 2. So you can define a trace.
Yeah, that's correct.
You didn't define your type 2, sorry.
So there is no profound classification. The classification is by properties. So what people who found the type 2 algebra, what they did was they took some system of matrix algebras, and they looked at it in the limit where the the entries in the matrix are infinite, and then they found an algebra with certain properties. It did not have Hilbert trace, space trace finite, but it was possible to come up with some other trace of the algebra which was finite. So you could have a density operator, you could do trace rho is equal to 1, you could do all that in the type 2 algebra. And then there are also algebras where you cannot do any of those. So they're classified based on their properties. Okay.
Maybe one way to say this, you look at a state which is almost a maximally mixed state. So you take a set of states, you look at a state which is maximally mixed, I mean, where every state has maximal entanglement with something, and then you look at states which are close to that, and the set of operators there is roughly like that. So it has a lot more entanglement in something.
Yeah, but if it's generic entanglement, it's type 3. Okay, so the operator that we are adding is the ADM.
I just want to understand if G tending to 0 is pretty sure. So here, when you say G tending to 0, you are removing the Hamiltonian constraint?
No, I'm not removing the Hamiltonian. I'm just going to, Planck length equals 0, classical.
Okay, so then you have the Hamiltonian.
Yes, we are going to come to the Hamiltonian constraint soon. So these people did not have a Hamiltonian constraint. So let's just go over it. I'll come to the Hamiltonian constraint. So, okay, so what they added was, they added one more operator to the right algebra, which is the right ADM Hamiltonian. And they also implemented a constraint, but it's not the Hamiltonian constraint. It is the constraint that this operator H hat, which is given like this in terms of T mu nu of all the fields, and V, which is the time translation killing field. So this operator is equal to the right ADM Hamiltonian minus the left ADM Hamiltonian. And there is a difference between the two signs here because this V, which is the killing vector, goes in opposite directions in the right and left half of the Schwarzschild diagram. So what we do is, we implement this H hat is equal to HR minus HL as a constraint. Now in Einstein gravity, of course, if you use the equation of motion, this is true. But what you're saying here is that H hat, which is the generator of this isometry, is related to the generators of time translations in the boundary. So actually, more precisely, what we add is this operator HR minus a constant M0, and that's only for the simple reason that we keep the horizon radius fixed, and you write your M as R plus by 2G, and in the limit that G goes to 0, you don't want it to blow up. So you subtract out this constant.
So, but in this Einstein gravity is not crucial, right? You say in Einstein gravity H hat is HR,
yeah,
for a general two-sided.
So if you take higher curvature gravity, you have an analog of this. The only thing is this HR and this HL will not be the ADM Hamiltonians which you have in Einstein gravity. So there will be some boundary terms at infinity which are, yeah, it is the Wald energy basically. So you can do all this for higher curvature gravity. This is just the ADM Hamiltonian which you get in Einstein gravity. If you write the Hamiltonian.
If you have high derivative collections, you might not change the boundary term usually.
No, you will get a slightly different boundary term.
Yeah.
In some cases, but like in string theory, for instance, we always expect it's like 0, 0 and this and now it's the stress tensor of the boundary. Maybe you
so this H hat, if you write this H hat in a arbitrary higher curvature gravity theory, it will reduce to a sum of two boundary terms, one at the right infinity, spatial infinity, and the other at left spatial infinity, but they will not be the usual ADM Hamiltonians. The ADM Hamiltonian, what you get when you take Einstein gravity, write down its Hamiltonian, and then look at the boundary term. Right? You will not get that. You will get something slightly different for that theory. Okay. So, yeah, sure.
So the fall off of the metric tensor and all that is assumed it's quite the same. You will get the ADM Hamiltonian. That's just boundary surface stuff.
Yeah, sure.
So
We are looking at asymptotically flat black holes.
Higher derivative gravity, what is the fall off?
Okay, so the way we did it, we didn't do it using the 3+1 decomposition. We used the covariant phase space formalism, where you explicitly get the boundary terms. So you have to assume, of course, that you are in some asymptotically flat spacetimes or something like that. But then the quickest way is to use the covariant phase space formalism.
You are saying that there are additional terms.
Yes, there are boundary terms. So this H hat will become a difference
Beyond
of.
ADM.
Yes, if you go to higher curvature.
For instance, let's say go to specimen gravity. So you're saying it would not just look like R to the D minus 2 times H00, but there would be other terms. Can you give an example?
In ADS, I haven't thought about ADS. We did it.
This is just in, I see. So you just want to be really in flat space.
Yes, in asymptotically flat spacetime, you can just use the covariant phase space formalism.
Now I'm a little confused. Because then, so there's still some boundary gauge that you choose at late times, right? On scribe, let's do some scribe. So on scribe, there's some boundary gauge we choose.
Okay.
And then there's a boundary mass. And are we saying the boundary mass is?
No, I'm just working in asymptotically flat spacetimes, and I'm using the covariant phase space formalism, where it is explicit that you will get this H hat as a difference of two boundary terms. Now it's complicated finding out what that boundary term is for a specific higher curvature gravity theory, but the beauty of the covariant phase space is that you don't have to worry about it case by case. You can just do it for an arbitrary diffeomorphism invariant theory.
I know, I understood that.
And then you can prove, okay, so that boundary term is called the canonical energy for that theory. You can just work with that exactly as you work with HR and HR.
I know, I'm just trying to get a concrete example of what it would look like in this, for instance, the boundary gauge.
Okay, I'm sorry, I don't have an explicit expression because we didn't need it. We were just doing it for any theory. But then the thing is, you just treat those two objects just like you treat HR and HV.
Okay, it will probably just have higher curvature.
No, but the curvature is not falling off. Everything is dying off. It's becoming very deep. So you have to have, I mean,
But you will have some explicit curvatures.
but everything basically will linearize. Right? That's why EDM Hamilton is linear.
Yeah, it's linearized, but it's a linearization of higher curvature.
But so it will in the end have to give you.
Yeah, it will be different.
Yeah, it will be linear. I think it will be linear.
Yeah, it will be linear in H, but I think it will have different terms.
The operator acting on the linear guy will be.
I mean, just thinking of it in 3+1 formulation, right? It will depend on what your Hamiltonian is, right? Your Hamiltonian will change from theory to theory. Right. Okay. So, so what I've done is I've told you that one operator is added to the right algebra, which is the right idiom Hamiltonian, and to the left you add the left idiom Hamiltonian, and you implement this constraint, which is h hat is equal to HR minus HR. Now you have to also expand the Hilbert space to get states on which this extra operator acts. So that you do by just taking your HQFT tensor with some space of square integrable functions of the conjugate variable to the idiom Hamiltonian, and that should be the time. So you should have a conjugate variable TR, which is the right time, and TL, which is the left time. But then we have a time translation symmetry in the space-time, which because the killing field generating the time translations goes one way in the right and the opposite way in the left. So what happens is when you do a time
Does this have to do with the complication? There's a difficulty in defining the initial value problem for these high derivations?
No, that is there. So I have to somehow, so actually the interesting thing is in covariant phase space formalism, you don't really explicitly assume that anywhere, right? You have a Lagrangian, okay, from there you do a prescription, which is this whole covariant phase space prescription to get the canonical energy. You don't really talk about the well-posedness problem there.
Yeah.
But I think that the problem is there, because even simply like, when you say the algebra of observables in some region is given by the algebra of observables on the Cauchy slice, the two algebras are the same. The domain of dependence of the Cauchy slice, if you have an algebra, that's the same as the algebra on that Cauchy slice. Well, that uses time evolution, right? So I think it is implicitly there in some way. Okay. So what you do is you add these, you expand your Hilbert space to add these left and right times. But then you have a time translation symmetry under TL going to TL plus C and TR going to TR minus C. So you can, for example, choose TR, C is equal to TR and set the TR to 0. So in a sense, there is only one conjugate variable once you have added this operator, that is TL plus TR. Okay, so, before I jump there, I just want to say something. So there is going to be something which is very crucial to the story. And the crucial thing is going to be that this operator H hat is a modular Hamiltonian. So I just have one slide where I define what is the modular Hamiltonian. I'm sorry, this is all, going to be very condensed, but I have to define the quantities which I talk about, so I'm doing that. So what you do is you start with an operator called the Tomita operator, which is an antilinear operator, and it acts on a special kind of state psi. And let me just write down the conditions for the state psi. So you have an algebra. For example, you have an algebra of the fields in the right exterior. Okay. So then what you do is you come up with a state in your Hilbert space which is such that A psi is dense in the Hilbert space, okay, for A in the algebra. Okay, so you take a state in your Hilbert space for which A psi is dense for all the A's in your algebra, and also, so this is called the cyclic condition. So dense means that you almost get all the operators, all the states in your Hilbert space by acting on the psi with the algebra elements A. And the fact that you have such a state is coming to you from the Riesz-Leiter theorem. So for example, in Minkowski spacetime, the Minkowski vacuum is such a state. In static spacetimes, there is a recent paper of Witten and Strohmeyer where they show this. So you have such a state. So what you do is you take a state which is cyclic, that is that A psi is dense, and then you want that A psi equals 0 implies A equals 0. This is called a separating state. Okay. So you take this cyclic separating state in your QFT, and then you define the operator S psi, which is associated to that state, which is such that S psi A psi is equal to A dagger psi, okay, for all A in your algebra. Then what you say is you say S psi is the Tomita operator associated with that algebra. And from this definition, it's clear that S psi square is 1, so S psi is invertible.
How do you know that this operator exists?
So let's take a very simple system like a finite dimensional Hilbert space. You can explicitly write down this operator for that. Okay. So for quantum field theories, it has been done by a lot of people. They have found out explicitly what is the state S psi.
It exists because the state is separate. So that's just a set of equations for S. That equation defines S.
Yeah, that equation defines S because A psi is dense in the Hilbert space. So you have told, we have told you how S psi acts on all the states of the Hilbert space.
Then you can solve the linear equations because of the second equation. You know, if you had 0 is equal to something, then you have an inconsistency. And the linear equations are solving those things.
Yeah, I think maybe his question was how horrible is it to find the psi? Yeah, yeah. Okay, so then because this operator is invertible, you have a polar decomposition for this operator, which is unique. So there is an anti-unitary operator J psi, and that multiplies something which is like the the amplitude delta psi to the half, and this delta psi is a positive operator. And delta psi is actually this S psi dagger psi, which I can also write because it's a positive operator. I can write it as e to the minus h, and this h is called the modular Hamiltonian. So delta is called the modular operator associated with the state psi, and h is called the modular Hamiltonian. So the interesting thing about this modular Hamiltonian is that it generates automorphisms of the algebra. So suppose you conjugate the algebra operator A with e to the ihs and e to the minus ihs on the right, where s is some real number, then this result is an A. So the modular operator is not in the algebra. The modular operator is actually unbounded. It's not in the algebra, it's not in the commutant algebra either. But if you do this conjugation, then this object is in the algebra. So the reason why we just went into these, yeah.
Was it obvious that the modular operator is not in the algebra?
Yes, it's not bounded. So the thing is, there is some, so let me just write S psi, A psi equals A dagger psi. Okay, this is the condition for S psi, right? Now what you can do is your A's are actually localized in some region, but you can construct an approximation to the annihilation operator in that region, and you can make this smaller and smaller. But this is not small. So this operator is not bounded. And similarly for delta.
Not just the boundedness, because delta psi is equal to psi.
Delta psi equals psi.
The algebra not be separating.
That's right. Delta psi is equal to psi. Yeah. Okay. Okay. So what I have done so far, so let me just explain why we went through this modular Hamiltonian bit. The reason is that operator H hat, which is the generator of the killing isometry in the quantum field theory, is precisely the modular Hamiltonian associated with a particular state of the QFT in the Schwarzschild background. This state is the analog of the Minkowski vacuum for a Schwarzschild black hole. It's the Hartle-Hawking state. And this H hat is a modular Hamiltonian for that state. Okay. So it's going to be crucial that this operator generates automorphisms of the algebra. Okay, so now we have an idea of what is the modular Hamiltonian. We have an idea of the extension of the Hilbert space and the extension of the algebra by Witten. Now let's define the cross product algebra. So I'm going to define both the cross product left and the right algebra. So what the cross product left algebra is you just take the left algebra operators, A prime, and then you dress them. Okay? So you dress them with this conjugation where H hat is your modular Hamiltonian and T left is the conjugate variable to this H left. Okay, so it's a very specific dressing that you do here. I just explained what is the importance of the dressing. And yeah,
Just can you go back?
sure.
Are you working at some, are you working in some fixed Cauchy slice, which is labeled by some time or something, in this whole consideration?
No, so you could work on a Cauchy slice, or you could work on the full domain of dependence of the Cauchy slice. The algebra is the same.
What I'm trying to, there's a reason I'm asking these questions, but the point is that this modular Hamiltonian doesn't seem to depend on the slice.
Okay, that's a good question. It does, actually it does. So it's a very important question. We are going to come to this later, where we will see a modular Hamiltonian which is going to actually depend on the slice. Okay. Now here it doesn't depend on the slice, and let me tell you why it doesn't depend on the slice. Let's just go back to the expression for H hat. So this is H hat, right? So H hat, V is a killing vector and T mu nu is conserved. So this is independent of the Cauchy slice. But then you will see cases where it is not independent of the Cauchy slice.
It depends on the algebra and the state.
No. What I'm saying is that this kind of a local expression, okay, that might or might not exist.
But is that the modular Hamiltonian only depends on the algebra and the state?
Yeah,
So
sure.
it might depend on what slice you use any slice.
Let me just think about that.
As you said, the causal diamond is the same algebra.
Yeah.
You define the algebra on one
Yeah.
side,
So if you,
slice will always be
sure, fine.
As long as
Yeah,
it's
sure.
the same.
Yeah. So, but there is going to be some operator which is going to depend on the Cauchy slice, which we are going to come to. But I agree with you that the modular Hamiltonian is for the full domain of dependence. Any Cauchy slice which ends at the 2 points is going to be the same. Okay.
Delta psi is not in the algebra.
Delta psi is not in the algebra.
Even if the algebra is the same, okay, it's not obvious that delta psi will.
No, delta is defined.
No, delta is defined for the algebra. So the delta is defined through the Tomita operator, which is defined given once you have the algebra.
So once you fix the algebra, then that's just.
So if you have an algebra on a particular Cauchy slice, by time evolution, you can always, just evolve it, and then that will be the algebra of the full domain of dependence. Okay. So here's the left algebra, which is this dressed operators here, and the left ADM Hamiltonian, and similarly for the right algebra. And we should remember that TL and TR are both not extra degrees of freedom. It's only one of, TL plus TR, which is a relevant degree of freedom. Okay, so TL is conjugate to HL, and they have a non-trivial commutation relation. So this algebra, this particular prescription is called the cross product. And the cross product would be true with whatever operator H hat we used. But when you have H hat, which is the modular Hamiltonian of some state, then this becomes special. Why? Because this cross product by the modular automorphism group makes the algebra type 2.
Sorry, I didn't understand. I thought TL was just a parameter.
No, TL is not a parameter. TL is the conjugate variable to HR and HL. So TL is conjugate to HL, TR is conjugate to HR, and that's very important for the story.
But when you say conjugate, do you mean?
They have a non-trivial commutation relation. Because I'm working with square integrable functions, I can just take TL, HL commutator to be I, but they have the non-trivial commutation relation, and that's very important for this consideration. I'm sorry? HL and HR, not HL minus M naught and HR minus M naught, because I've just subtracted by some arbitrary M naught. So it could be more or it could be less. So that's what I'm adding, so that can be positive or negative.
So that's what allows you to define conjugate, because usually we say can't define a conjugate Hamiltonian because Hamiltonian has a lower power.
Okay.
That's what we usually say in quantum case, undefined line operator. because time operator would translate you and it would just you can just go to negative energies if you have such an operator.
So this one can be positive or negative.
So is it because that we have subtracted out M naught to define a time operator?
Maybe I have not thought about
I think
that.
one way to see it is that if you look eternal black holes, so it looks like e to the minus beta e by 2 EE. Now you time translate that state. So then now it looks like e to the minus beta e by 2 plus IEE EE. That state, that's that time operator, that E. And the edge here is actually not bounded below because its expectation value is very large. Is the black hole. So unless you go to order n square, you can lower the energy. You can go positive or negative. Of course, eventually it is bounded below the type 1 distance. Perturbation theory, you can see that.
Yes, it's bounded only the type 1 distance.
So that's the time operator is literally this. It's the shift of the two sides of the eternal black hole relative to each other.
Okay, now let me just come to the reason for this dressing and this dressing by this H hat. So the thing is, by construction, the dressed operators commute with the constraint. Why they do that is because this operator, this dressed operator, its commutator with H hat is not 0. Okay, you know what its commutator with H hat is because this is H hat coming here. But its commutator with HL is also not 0 and the two will cancel out each other. That's the reason for the dressing. You want, there is a reason why we want this thing to happen. The reason is that if we are going to implement this H hat plus HL minus HR as a constraint, then I want my operators in the algebra to commute with the constraint. So now they do it by construction.
Here, A is really what? A prime. It's in the left algebra.
Sorry, that was a typo. That's in the left algebra. Okay, so the type 2 algebra has a trace. Now that we have gone to type 2, so by doing this cross product with the modular Hamiltonian, you go to type 2. So now that you have a type 2, you have a trace, which is an explicit linear functional on the algebra, such that trace AB is equal to trace BA. But this need not be the Hilbert space trace, which could be infinite. So I'll just show you this trace, what it looks like. Let's call the left Hamiltonian as X, okay, and HR is H hat plus X. Then you can expand this any.
Can I ask a question? If your statement is really going to be about the right algebra, so A prime is its commutant.
A prime is its commutant.
If you ever need A prime principally, or you could just forget about the commutant.
You could just forget about the. Yeah, I mean, it is Witten's convention to add this variable as X and then to write HR as H hat minus X.
And that is okay, but if all of that you could do just on the right side without saying anything much about HL, without ever talking about the
Yeah, we don't need really anything about the commutant. Okay, so the algebra, the operator in the extended algebra can be Fourier expanded in this way, and then the trace is given by this expression. So this is the trace of the operator in the extended algebra, and the psi is a special state. It's the Hartle-Hawking state of the quantum field in the Schwarzschild spacetime. It's like the Minkowski vacuum for Schwarzschild. And then obviously you want some properties of this A hat. It should have a non-trivial dependence on X so that this thing is finite. Okay, so this is a trace and it obeys the property trace AB is equal to trace B. Now you can define a density matrix given this trace. So what you do is you use the same formula which you use, for example, in quantum mechanics. Trace of rho A is equal to A expectation value in the state, and that's the rho of that state. But the only difference is this trace is not the Hilbert space trace. This is the new trace we just defined. Now you have density matrices, and with that you can have the entropy of the algebra, which is this von Neumann entropy of the density matrix. So for the particular type 2 algebra that we started out with, which has trivial center, the trace is actually unique up to a scaling by a constant, and that constant can actually shift the algebra entropy. So the algebra entropy is only defined up to a constant. Okay, so the final thing I want to say about this work of Witten and collaborators was that they showed that the algebra entropy is equal to the generalized entropy plus a constant. Okay, where the generalized entropy will have actually a different value evaluated where you evaluate it on the horizon. So we evaluate it at the bifurcation surface. So the algebra entropy is the generalized entropy of the bifurcation surface plus a constant.
So S generalized, in my limited understanding, is the area divided by G.
Plus the entanglement entropy.
Volume term.
Entanglement entropy.
Yeah, that's right. So, as you said before, I mean, G is cutoff dependent, and the cutoff dependence is sort of cancel out. So there's some idea of renormalization of the.
There's some idea that that total quantity is well behaved.
I mean, but do these people actually really find that by S-gen it's that formula that everybody?
Yes. It's exactly that formula. It's the area by 4G plus the entanglement entropy.
That comes by imposing the equations of motion. The algebra itself doesn't know about the here.
No, yeah, so basically you use the Raychaudhuri equation to integrate the Raychaudhuri equation to get the difference of areas.
It's the fact that the modular Hamiltonian knows about that. It's not that surprising that you get it.
What is worrying me is this business of the fact that S-gen, I mean, we have defined in terms of cutoffs actually.
Yeah, but now you're getting this combined quantity out of a type 2 algebra in which everything is finite.
I understand that it's some very weak result that somehow you doesn't think.
I'm not sure it's that deep. No, I'm not sure it's that deep. I think that it's a nice way of regularizing. Like this type 2 language is a way of saying where Susskind and Hugo was saying, we have some divergences, we cut it off. Here's a way of saying, a more fancy way of saying, you define a trace on a type 2 algebra and that actually regularizes the over 4G and this together.
Does it regularize or you just get some real finite object to compute?
It's not magical.
No, it is finite quantities. In type 2 algebra, everything will come out to be finite quantities.
Left-hand side is finite, there's some proof for it.
The fact
that it's cutoff independent, there's no notion of cutoff, that's what I'm trying to say. And that's.
Yeah, it's a canonical way of regulating maybe over 4G plus S.
A way which includes gravity in a natural way.
I mean, it's a canonical saying that Susskind and Hugo would have criticized by saying, how do you know that you cut them off at the both ends? Kind of a canonical way. Maybe that's what I'm saying.
I mean, I understand this in terms of Rooter-Gangnaghi surface, where the divergence is proportional to the area, etc. I mean, it's a known calculation. But there is no cutoff on the left-hand side. No, I'm just trying to say whether this is a very general, something very general is happening here in quantum gravity.
But first of all, it's not that in Rooter-Gangnaghi often try to compute the absolute entropy. So they don't have that entropy. That C could be infinity or could be whatever.
Yeah, C is actually a constant which could be of the order 1 by G, and when the limit when G goes to 0, it could be infinite.
So what you're really saying is how the generalized second law is defined. If you throw in some stuff into the black hole, then the change in the entropy, that is finite before and after you throw in the stuff. It's not that the whole entropy is finite, which is what you're trying to measure in the Rooter-Gangnaghi. So you look at one state and another state with a small perturbation or drop. And the change in the entropy, this delta is finite. And it's I also thought it was very magical, but now I came to the conclusion that it's not so. It's kind of coming from the equations. That's my idea. I don't know, you guess.
Okay, so this result, by the way, is not true for general states. It's only true for something called a semi-classical state, which is a state in which the fluctuations of the p are very small. Okay, so the p is the variable which is conjugate to the new ADM Hamiltonian that you have put, and the fluctuations in p are small. So we want fluctuations in geometry also to be small. So it is for those states that they found this result. It's not true if you go to more general states. So what they show explicitly is for those states that the algebra entropy is equal to something called the relative entropy between two states in a quantum field theory, plus some other terms, plus order epsilon terms, where the epsilon is the small number that you have introduced to say the fluctuation is of order epsilon. Okay. So this S relative is the relative entropy, which is defined usually for quantum systems like this: trace rho log rho phi log rho phi minus trace rho phi log rho psi. Okay, and there is a generalization of this formula when the Hilbert space trace is infinite. So that is this quantity, relative entropy.
So is this the thing that is capturing the state dependence of the generalized entropy?
Yes, yes.
This relative entropy?
Yes, exactly. Exactly.
the state.
Yeah. This phi is precisely that state, right, for which you are, well, what did I do? Yeah. So let me just do Control L. Control L.
So the A over 4 Newton is then in the other terms?
No, it's actually in the relative entropy. So the relative entropy is related to a difference in areas between two cuts of the black hole horizon. And then there are some other terms which are listed here, which cancel out the area by 4G contribution from one of them. So it's really S relative is related to area at infinity minus area at the bifurcation surface, and the other terms all give you precisely the area at infinity, and they cancel that out. So you're left with only the generalized entropy at the bifurcation surface.
So this, how is this different from Cassini's observations? So Cassini also has.
What was his observation?
I thought it was very similar to this, but that's what I.
So this is actually from a paper by Wall, and I don't think anyone did that before Wall did that. So he just looked at the semi-classical Raychaudhuri equation, and by integrating it, he was able to prove that relative entropy is related to difference of areas. So I don't think anyone did that before Wall, this particular calculation. Okay, so that's exactly what I have here. S gen infinity minus S gen B is the relative entropy. So from there, these people were able to deduce that the algebra entropy is the generalized entropy modulo a constant. Okay, then they used the monotonicity of the algebra entropy to show that generalized entropy increases between early and late times, provided the black hole is allowed to equilibrate in between.
Monotonicity of the algebra entropy, is that something?
That's the monotonicity. Let me just say what this monotonicity result is. So you take the algebra entropy for some state and for the algebra A, and you take the algebra entropy for the same state for the algebra B, which is a subset of algebra A, and then provided you normalize your trace in such a way that trace is the same for both the algebras, you get the mono. Yeah.
The second one is less than
Yes. Okay. So what I want to do next is I want to discuss a proposal which came last year for the entropy of any subregion. Okay, so what I mean by any subregion in any spacetime need not be a black hole spacetime. The subregion is basically just the domain of dependence of some partial Cauchy slice. Okay, so this could be the region. It could also be an infinite wedge like this. It could be any such region. Okay, and the proposal was that we will associate an entropy with the algebra of observables in that subregion. Okay, so I'll just go a little bit quick over the first point. We have already seen that. So what these people do, the new thing that these people do is they impose the Hamiltonian as a constraint. Okay, so the Hamiltonian that they impose as a constraint is basically something which generates the flow of a particular class of diffeomorphisms. So their idea was that if you write your metric as some background metric plus graviton perturbations, then you still have the gauge freedom to keep this the same but change this, right? By taking diffeomorphisms of this order of H, you can change H, but you can preserve the split. So their idea was that we should have the invariance under this class of diffeomorphisms to be imposed as a constraint. Okay. So this class of diffeomorphisms which they took was a very particular class which preserves the subregion and it also preserves its causal complement. Now you could ask here, why can I not do this for every diffeomorphism? Yes, we can. Now their construction was for the special class, and so the advantage of their particular construction was that for that special class, they got exactly the result which Witten got, which is that the algebra entropy is the generalized entropy of that region plus a constant.
So I just wanted to understand something. Saying that it's a type 3 algebra is a graviton, you did as quantum field, but without the Hamiltonian constraint.
without the constraint. Now their argument is that you have to have a constraint because your perturbative theory has to be embedded in a nonlinear theory. So you could still have, so if this was your Planck length, then you could still have a psi of order this, which affects this but does not affect this, right? So you should impose that as a constraint.
But this constraint that you're imposing, they impose, is it addition to the Hamiltonian constraint or?
No, this is the Hamiltonian constraint. So it is, let me tell you what exactly it is. You're imposing the generator of this diffeomorphism, this particular diffeomorphism, class of diffeomorphism that they do. The generator of that diffeomorphism on the Cauchy slice is being imposed as a constraint.
So general diffeomorphism which preserves the Cauchy slice?
Which preserves the region. So you are trying to define entropy for some region, right? So let's say you want to define the entropy for this region, okay? So the diffeomorphism, let me draw it. It's there in my slide, but let me draw it again. So this diffeomorphism will go like this, okay? It will preserve the region, it will not change it. And here it will go, here it goes up and here it goes down. It will do exactly what the killing vector does, but it's not a killing vector. It's just another diffeomorphism. So what Witten did was he imposed a killing isometry as a constraint. Here you impose a constraint for any diffeomorphism.
Can I say something which I think is important?
Yeah.
Because I think it's not the entropy, it's actually entropy difference.
Yeah, again it's entropy differences. Sorry, you're right. It's not the absolute entropy.
It's important for the following reason. You cannot actually define this entropy about empty space, for instance. Because those regions, in fact, as you do them themselves, are not diffeomorphism in nature.
Yeah, they're not.
It's very important in this paper that there's an observer in this.
Yeah, we are going to come to the observer.
So the heavy observer is what makes them.
Yeah, sure. The observer defines the region for you in a sense. And that's the entropy associated to that observer.
It's actually entropy associated with small fluctuations above the observer.
Yeah, that's right. Okay, so so they implement this set of diffeomorphisms as a constraint, and here I've just given a sketch again of the way that particular diffeomorphism goes. So the vector field, suppose you take this diamond, then the vector field is null on the boundaries of the diamond, and inside it goes just like your killing field does. Here in the complement wedge, it goes in the opposite way. Okay? So these, and there are some more assumptions. This diffeomorphisms must behave like, so here is your entangling surface. The diffeomorphism must behave like the killing isometry of Rindler's space in the local Lorentz frame at the entangling surface. Okay, so as Suvrat just said, this constraint cannot be imposed. You will get something trivial if you try to impose this constraint on this states. So it can be imposed only by adding one more degree of freedom, which is that of an observer. So we will take the observer to be just someone who has an energy Q which is greater than or equal to 0. And because Q is an energy, I have to implement the constraint which is H plus Q minus Q prime, where Q prime is a similar observer in the commutant wedge. Okay, and the minus comes because this vector field goes in the opposite way in both the regions. So that's what you have to, the bulk part of H plus Q minus Q prime is what you have to impose as a constraint. And let me remind you again, H is the generator of this flow on the Cauchy slice.
So when you say becomes actually becomes trivial, is the algebra is empty?
No. So what, if you look at those operators which commute with the constraint, or you look at those states on which when the constraint acts you get 0, those are trivial.
Right, because in the sense that the ones commute are just
Yes,
right?
yes.
Because of all these results, yeah, if you look at the algebra outside, it can see it. So you have to, and it can still see inside the presence of the observer, but not in perturbation.
Yeah.
So in perturbation, maybe you can hide it.
Okay, so the constraint that is imposed is this, and we need the algebra of operators which commute with the constraint, and now what we do is we just dress our operators in such a way, so you add this operator which is the observer, you add the observer degree of freedom to your original algebra of this region, whatever this region is, okay, and then what you do is you dress your algebra operators A in such a way that this operator naturally commutes with this. okay, because you want the algebra of operators which commute with the constraint. Then what you can do is you can take the double commutant of this algebra generated by this set, and that is a cross product algebra, which you can see by construction. But it's a general cross product algebra. We have not said anything as so far about this H being a modular Hamiltonian. Only if it's a modular Hamiltonian will you get a type 2 algebra. So a crucial assumption of these people is that H, which is a local integral on some Cauchy slice, is indeed a modular Hamiltonian associated to some state. Okay, so that's an assumption that they make, and then the diffeomorphism is not an isometry. So the value of this Hamiltonian will depend on the choice of Cauchy slice. Okay, so if you assume that H is a modular Hamiltonian of some state, so going back to this question here, so here is where we have a dependence on the Cauchy slice. Okay. So if you assume that H is a modular Hamiltonian of some state, then this cross product algebra becomes type 2, just as we saw. Okay. And then you have a trace on the algebra, you have renormalized density matrices, you have an entropy and so on. And you get exactly what Witten got, which is that the algebra entropy is the modulo constant is the generalized entropy on that Cauchy slice. Okay, so the crucial assumption of these people is that H is a modular Hamiltonian for some state. Okay? This is very hard to check because modular Hamiltonians are hard to compute, and the problem is that they are generically non-local. Usually they are not written except in special cases as an integral over a Cauchy slice.
I have a question here. Is it important that it should be the modular Hamiltonian as long as it's in the modular automorphism? Wouldn't you still get type 2 algebra and trace?
Yeah, modular automorphism means flow generated by a modular Hamiltonian. It could be of any state, that is true.
Yeah, it could be a modular Hamiltonian of some other state.
Yeah, any state. It will not be modular Hamiltonian of the vacuum, actually.
No, certainly not of the vacuum.
Yeah, it will be of some other state.
It could even be, if you're in state A, it could be modular Hamiltonian of state B also.
Yes, it could be.
So that, yeah, I was also having, because you define the modular Hamiltonian through this Tomita operator.
Through the state, but
not through the density
yes.
matrix,
Yes.
the way in which people normally
Not the path integral method.
So you're saying that given a state, supposing I had an operator S psi, and you define the corresponding delta psi, then that delta psi would be associated with some other psi prime.
Doesn't matter. It will still make it type 2.
But there will be a
It will still make it type 2. It will still make it type 2. You just need one modular Hamiltonian associated to some state.
That's what this is. In general, the S that she defined, that's rho times rho inverse. It's rho on the algebra and rho inverse in the show. That you can
rho
show.
means
Delta, not S, delta. Delta.
Delta.
Modular
Yes,
operator.
so the S, the delta that is given by looking norm of S factor S.
Yeah, that is
rho
a.
on the algebra and rho inverse. That you can show.
Oh, I see.
It factors
And the same.
on the same state. But I just thought what your question was is that you can take the modular Hamiltonian associated to any state, and you can do this modular automorphism, and then you will get a type 2 algebra. You just need for modular Hamiltonian of some state.
The modular automorphism is just this e to the I.
Yes, IHS A e to the minus IHS.
So what is this non-local?
I'm sorry.
You said non-local.
Non-local, by local here I mean an integral of the Cauchy slice.
What is it written as?
Yeah, so if it's non-local, it will be an integral over different slices. Okay, it will not be an integral over one Cauchy slice. For example, it could be, say you are here in Rindler, it could be an integral over this slice plus an integral over this horizon plus some other integral over this horizon. Okay. Now there is one instance where this assumption of these people is exactly true. That is that the generator of the flow of the diffeomorphism on a Cauchy slice is exactly a modular Hamiltonian, and that happens when the subregions are specific wedges in black hole spacetimes. Yeah, so let me just show you the wedge here. So here you have the full right exterior of the black hole, and then you have a wedge B which is given by the cut here at B star. Okay? So these are examples of wedges A and B. Now what happens is that in this case, there is a property called a half-sided modular inclusion. So the smaller wedge is the half-sided modular inclusion of the algebra of the larger wedge. Okay, so I'm going to just tell you what this is.
Sorry.
Oh, yeah.
Are you saying something that's going beyond the Jensen-Speranza paper?
Yes.
This was not in there.
This was not in there. This was in our paper. Okay, but this half-sided modular inclusion is known from before.
Yeah, but this observation that their construction would work for you.
Yeah,
not in there.
It was not in the paper. So now what you do is, let's say for this wedge A, which is the full right exterior, you know the modular Hamiltonian corresponding to the Hartle-Hawking state. You know it because we have just seen it, okay? So we know this. The question is, can we find out the modular Hamiltonian of the algebra B, okay? And the way you can do this is, let me just, Okay, so let me just talk about what that half-sided modular inclusion is. It is a subalgebra of A, which we have, what we have in mind is that B, such that the vacuum or the Hartle-Hawking state is cyclic and separating for B as well, which is true, we know that. Then what you do is you take the modular flow generated by the modular operator of A, and then you conjugate it like this with the operators in B, and suppose the result is a subset of B for T either positive or negative, then we call it a half-sided modular inclusion. And let me go back to the figure here. So what actually happens is that you know that the modular Hamiltonian generates the flow of this killing field, okay? And you can see that when T is positive, when your real parameter is positive, then it pushes points inside B. So it keeps B in B, okay? So the way this acts on the operators, of course, is, by the way it acts on points, and then it keeps you within B. So this is a half-sided modular inclusion of A. And the advantage is that then you are guaranteed, the existence of a unitary operator which looks like this, okay, where this E V star is a positive operator. And then furthermore, the unitary obeys the equation that the subalgebra B is given like this in terms of the algebra A. Okay. So it satisfies some other properties also which don't concern us now. We want the modular Hamiltonian of B, that's what we want. Now on the horizon, we know that U is a null translation because it's the null translation which takes the wedge A into the wedge B. Okay, so we know what U is, it's a generator of the null translation. So that's how I'm able to write EV star on the horizon, not anywhere else. Anywhere else it will be quite complicated. So what you can show then is that you can get the modular Hamiltonian of B from the modular Hamiltonian of A and this operator. Okay? So this has been done by a lot of people before, and this is a neat expression which gives you KB. Okay? So let's write down what KB looks like. So what I have done here is I have written the modular Hamiltonian on both H plus, which part of H plus which starts at V star, and Scri plus. Okay? And this is what it looks like.
For this, is it important that the entire geometry has a killing symmetry?
It's not. Actually, for Kerr, the entire geometry does not have a time-like killing vector field in the right exterior of Kerr, because the killing vector for which it's a killing horizon is not time-like in the interior. Okay, so it's not. You only need it for the Cauchy slice. I will choose my Cauchy slice to be the horizon plus Scri plus.
What I'm thinking about is a case where there's some stuff that's floating about outside the black.
Okay.
In that kind of a state, where there's a black hole and maybe some other perturbation around it, is this formula still true that you have this simple relation between the modular Hamiltonians?
Is this formula still true?
Someone seems too good to be true.
So this formula is for the QFT modular Hamiltonian in a region of spacetime. So it should be true, right?
So it would be true, for instance, in a Minkowski vacuum, right?
Yeah, it would be true in Minkowski vacuum.
But now let's say I took an excited state in Minkowski, then it might not be true, right?
Let me just say, okay, so the statement is, if I have Ka, then I can find Kb. Now I have to tell you for which state I find the Ka. Okay, so I don't know Ka for excited states. I know Ka for Hartle-Hawking state, so that's what I will use.
But you're saying the relationship between KB
And Ka is true for any state.
that's always true. It's
Yes.
always given by this.
Yes, exactly. Okay. So let me just show you the expression for K. Okay, the expression for this looks like this. And what is interesting is that this yeah, any question?
I think it's probably true that there's always this epsilon and there's this relation.
Yes.
But epsilon is a single integral is.
No, that is not there. That's not, even in this case, you see when you go in the bulk, it's not true. It's only true on the horizon. That it's simple, it's not simple.
That's a very special thing.
Yes, yes.
True on the horizon means what? It's algebra of the whole range. So either it's true or it's not true, right? Because we have the whole range. So we have a modular Hamiltonian.
No, but the expression for the modular Hamiltonian on the horizon is a local integral. It's not local outside. So this result is still true.
No, but I don't need it outside. That's enough.
Yes, that is enough. That is also correct. That's also true. If you think of it as a Cauchy slice, that's enough.
You're saying if you give me the full modular Hamiltonian, I can get
So,
to any range.
yeah. So what I'm saying is that in JSS, for example, they have any Cauchy slice. Okay. So if I had any other Cauchy slice, I would not be able to write it down in closed form as a local integral.
I can see where you're going with this to prove the monotonicity, which is what you want to prove. So
Yeah.
for that you only need the relationship between
Yes.
modular Hamiltonian.
Yes. I only want to use the fact that the Cauchy slice is H plus union Scri plus.
I understand, but you're saying this relation for epsilon is always true. Right?
It's always true. Exactly. It's always true.
No, I'm trying to, like your question. It is not vacuum. I'm not sure.
But this is
No, if it's not vacuum, I don't know what K is. That's what I'm saying.
No, you don't know what to do, but is this epsilon?
Yes, this is true. This is true. This is true, yes. There should be a cyclic separating vector which is common to both algebras.
So statement seems to be that in a black hole, if you have stuff floating about, you do a weight. This is still true. That's not.
This I am not. This is not.
It somehow seems very confusing, right? For the following reason. Let's say I have a black hole and I have a shock wave which is kind of going in. And I move my wedge so that I cross the shock wave. So I look at a wedge which doesn't include the shock. And I guess the statement is that you still know the modular Hamiltonian, even though both of them are now pretty complicated.
Yeah.
But somehow the relationship is always this very
The relationship is true for any cyclic separating state which is common to both algebras.
You know how we prove this? Like how is this proved?
Unfortunately, it's not trivial. I have looked at it once, but long while ago.
I can read this in a positive operator. There's some influence stuff. That it should be simply related to the electron difference.
No, it's KB and KA, but B is related to A by the unitary. Yeah, so if it is a half-sided modular inclusion, then it's true.
So let's say we assume all that. Let's say if you have a complicated matrix theory, I would have thought the epsilon B went on like created some complicated state.
Yeah, it will be different from theory to theory, obviously.
So
If you had a interacting
then the
theory,
K will be different, but I would have thought even epsilon B will also be different.
epsilon V will also be different. That is
And
true.
it won't be given by local integral.
Well, if you have the Hartle-Hawking state, it is given by this.
Yeah, that I agree.
Yeah, on the horizon. It's not a local integral if you go away from the horizon. Yeah,
If you have Hartle-Hawking state, you get the integral.
yeah.
But yeah, okay. Yeah, that is okay.
No, but now it seems to me later you would want to use this to prove the generalized second.
Yeah.
But then you want this to be true for all kinds of states, not just for the Hartle, because the
No.
Hartle state is nothing.
No, this is the modular Hamiltonian for a particular state, which is only going to be used for getting type 2. I can take any modular Hamiltonian to get a type 2. So the type 2 construction of JSS requires a special state. It is not the state of the quantum fields in which you are computing the entropy, but it is an auxiliary state which you need to do the finiteness. You need to make it type 2. Okay, so that's the
You
thing.
never need the fact that the modular Hamiltonian of the wedge, the difference is given by this local integral. You will never use that.
No, we will use that because this is the generator of the flow, right? So this is the generator of the flow of this vector field V minus V star d by dV on the horizon. Okay, this has exactly the JSS form.
I know, but what's confusing?
So what we are going to do is we are going to impose V minus V star d by dV flow as a constraint. You can just do everything which GSS did because this vector field obeys all their conditions. And this is a modular Hamiltonian, which is a conjecture in their paper, but this is a setting for which it's exactly true. Okay. So we can apply the entire analysis of GSS to this problem. And so here I just want to come to some small comments. Now for finite regions, GSS actually add an observer to the system as we saw. The observer defines that region for you. Now for wedges with asymptotic boundaries, what they proposed was adding the ADM mass as the operator, and this plays the role of the observer. But the problem is that when we consider our wedges, which is the wedge A and the wedge B, we have an issue. The same ADM operator would be added to both the wedges and operators dressed to this operator. Okay? So the ADM operator is really not associated with that wedge. So to make the dressing specific to the wedge we are considering, we add an observer and construct the cross product algebra with respect to the observer, adding the ADM mass as well as a simple tensor product. Okay? So you'll get a long constraint. And when we wrote an earlier version of the paper, we had done what GSS had done, and it was pointed out to us by Witten that if you take the the modular operator, modular Hamiltonian, it does not have a split into something in the algebra and something in the commutant for anything other than the full right wedge. Okay, so if you just take a wedge which, say in the Schwarzschild, you take two wedges, one which looks like this and one which looks like this. Both of them, in the GSS prescription, you will add the same ADM operator. So that's why we added an observer. So now you don't have a situation where the modular operator splits into something which is a boundary term which depends on that algebra and the operator which and the piece which depends on the commutant. Okay, so that is the small change that we have done. I'm sorry?
It's an observer, not an asymptotic observer.
Not an asymptotic observer.
It's an observer at some finite.
Yeah. It could even be an asymptotic observer, but it is connected with that particular wedge. It's not HADM, which doesn't care about the wedge. In the construction which they had, the problem is when you compare across two wedges, you have the same HADM. Okay, the vector field looks the same at spatial infinity. That's the problem. I'm sorry?
Why is that a problem?
That is a problem. So you want to make it the dressings specific to the region you're considering. Okay, and what Witten had pointed out was that if you look at the boundary theory, then this is your modular Hamiltonian. It has a split into HR minus HL, where this is an operator which can be measured by an observer in the full right wedge, and this is an operator which can be measured by an observer in the full left wedge, not these wedges.
Yes.
That's the issue.
I'm a little confused about something.
Yeah.
The reason you need an observation, the way I think about it, is that you need to define the region.
Exactly.
However, in this case, the region is well defined. It's an asymptotic region, so you can define it as scry minus. And scry minus, I think, is defined because scry minus is well defined.
Yeah, scry minus is well
So I
defined.
need to say, look at the wedge here goes, look at the light ray that starts at a given value of.
Yeah, which is exactly what I'm also proposing.
Then you don't need
No, it's not HADM. See, the only thing is if you put HADM as the, so let me write down that HADM. So that HADM is an integral over the sphere at spatial infinity, which depends on something times the vector field, okay? Now the vector field, you have to say how the vector field behaves asymptotically at infinity, okay? So that always in source JSS paper, the vector field always behaves the same way in all the wedges.
I see, but in this case, this vector field is spatial infinity, right?
Exactly. So what I'm saying is that, you see, you use the vector field to define the whole wedge, right? You say that the vector field preserves that wedge. But if you have an asymptotic, you have an operator which is defined at the sphere at infinity, you put the vector field there, it's the same vector field. The vector field behaves the same in both the wedges. That's the problem.
Maybe another way to say this, maybe I can see. The point you might be maybe you're saying is that I see. If you try to define I see now the point. If you try to define the algebra of the top wedge, like from there to the
Yes,
top point,
yes,
and you use this edge,
Yes.
you can actually use it to evolve past.
Yes.
You can use it to evaluate.
Exactly.
This algebra is not closed under product.
Yes.
In fact, this algebra seems to be the algebra of a wedge might seem to be the whole algebra.
Whole algebra, which is what Witten was, which is exactly, which is what Witten was saying, doesn't have a split into something which observer on the right algebra and the left algebra measure. So now you can just add all these things and you can ensure that the algebra commutes with the constraint. Okay, so here is my whole algebra here. So the dressed operators where H is actually your curve.
Adding an observer counts as
Yeah, I think it's
not a whole.
yeah.
No, it's okay. Adding an observer defines the wedge for you. And then what, let me write the constraint. Let me write the constraint actually. So H plus Q minus Q prime plus H ADM minus H ADM prime. Okay. Now, what you can see when you have this constraint being satisfied, yeah.
Q is the Hamiltonian of the observer.
Yeah, sorry. Q is the Hamiltonian of the observer. Q prime is the observer in the commutant wedge. Okay. Now this H, what is this? H is actually the modular Hamiltonian. So the way, when you implement this constraint, it is not needed, it's not true that the modular Hamiltonian splits into sum of two boundary terms, one of which is associated with the right wedge and the other which is associated with the left wedge. So we have this observer here as well. Yeah.
How does it, but it seems to me that if you're saying that you cannot use this to complete the algebra.
No, you can. So that's what I did. So this is the algebra.
It's like what you're doing. Let's say you want to define in PDS the algebra for the subregion. And you dress operators to the observer and then you work in subdivision. In this case, if you just naively took that picture, the full algebra, you would take the ADM Hamiltonian, it would move you along the
Exactly.
So you're going to dress.
So the problem which Suvrat is saying is exactly the problem which Chandrasekhar, Pennington and Witten had found, which is why they had to do this long GSL procedure using early times, late times and stuff like that. Okay, so sorry, I'm running out of time. Should I, it's just, tell me when I have to stop, okay? Okay, so the algebra is still type 2. And then the only difference when we want to compute the monotonicity, we don't look at the algebra entropy. Again, we look at the relative entropy between two states. And the two states which we choose have the same parts for the other degrees of freedom, which is G and F. G is related to the observer degree of freedom and F is related to the ADM degree of freedom. So those are the same for both the states. This phi is going to be the state of the QFT. This omega is going to be the state which you use to create the cross product. Okay. So G is observer degree of freedom and we take it to be a semi-classical state. Then we can show, of course, that the relative entropy of phi hat with psi hat, omega hat is the same as S phi psi. And this is the type 3 relative entropy and that's clearly finite. So then we get an expression for the relative entropy from the JSS construction, which looks like this, where the operator K I had already showed you is the modular Hamiltonian. Okay, this is K for the state phi, this is K for the state Hartle-Hawking. And this is the entanglement entropy in the state phi and this is in the Hartle-Hawking state. Finally, what JSS do is that they impose the constraint along a partial Cauchy slice. So you have a Cauchy slice of the region you're considering and then you have a Cauchy slice corresponding to the complement region. Okay? So if you implement the constraint on the partial Cauchy slice, then you get the area, sorry, I went too fast. So you get the area, okay, area of the entangling surface. So if you have a entangling surface is the surface here, get the area of the entangling surface. Okay. And,
it's obvious that the relative entropy is monotonic. That's the fact of the model.
That is what we are going to use, exactly.
But now you want to argue actually that the generalized
entropy is monotonic, so I have to get the area somehow. Okay, so what I'm saying is if you implement the constraint, see the way Wall got the areas was by integrating the Raychaudhuri equation. Now what I do is I implement the constraint on a partial Cauchy slice, that gives me the area term. And then what I can do is I can write KV in terms of the area and put it here.
The observer somehow important.
The observer is not important in relative entropy because just I just showed you that the relative entropy of for the two states we are considering, the relative entropy of the type 2 algebra is the same as that of the type 3 algebra.
What if the observer some field?
Observer will all cancel. So the observer degrees of freedom between phi and psi cancel out.
We want you to cancel across different wedges, right?
Exactly. No, not even across different wedges. They cancel out in a single wedge.
In a single wedge, I thought you could only find delta S. The change in entropy.
Yeah, just let me just show you the expression again. Let me just show you that. Yeah, so here is the expression. You see what I'm going to do? I'm going to substitute for k from this equation and put it here, right? Now you have the two states have the same g and the same f. That is important, of course. If I change the g and f, if I change the observer degree of freedom and the ADM degree of freedom, if I compare two states where those were different, then I agree.
The question is, as you change b, you want this q term to not change as a function of p.
No, wait. So this thing, see, you put this in the relative entropy, right? It cancels out between this term and this term. It's not even there because this is actually the type 3 relative entropy. It should not be there.
No, the relative entropy is not there.
Yeah, the relative entropy is what we are going to use. Okay, so let me just show you the result. So this cancels out in the relative entropy in a single wedge, and relative entropy at V star, because of the areas, you already saw the areas, can actually be written as S gen infinity minus S gen V star. Yeah.
This term, it seems to be somewhere that the observer should be important in this relation between the relative entropy and the
See, the thing is, when I put the observer degrees of freedom the same, then in the relative entropy it will not be there because this is type 3 relative entropy.
What if the observer was falling in? The observer was a heavy field.
Okay.
Some of it was
No, we are always working in. No, we are working in an approximation in which the observer is not strongly coupled with the quantum field theory. So this semi-classical states.
I know, but it doesn't have to be strongly coupled. Some of it could just be falling into the black hole. Like it's
Okay, so
falling in. And then I would worry that somehow this maybe I'm not thinking very clearly, but I would worry about
I don't know if.
observer degree of freedom changes.
Okay, I haven't thought about that because I'm in a single wedge, it doesn't matter because I'm comparing two states, so the observer degrees of freedom will just cancel out.
But you want to compare across wedges.
Yeah, so they cancel out in a single wedge. I get the equation corresponding to that wedge, and then I take the next wedge. It's just a relation between the generalized entropies that I need, right?
No, in that relation, can you go to the next one?
Yeah, let's go to the next one.
This one.
Yeah.
You see, this is between a different value of E and a different value of V.
Sure.
At every stage, with the relation between.
Okay, so let me, wait. No. So let me, I have skipped some steps here. So, okay, so what are the steps which I skipped? You see, when you have the K V star corresponding to the Hartle-Hawking state, that corresponds to some area in the Hartle-Hawking state, okay? That's just area associated with that state. Now what I use is, I use that the Hartle-Hawking state is invariant under time translation, okay? So the area associated with the Hartle-Hawking state is the same as the area at infinity because I want my black hole to settle down to a stationary state. That's what I'm using. That's how I get infinity. So I get it from this single relation. In this relation, all I have done, I've replaced K by A, okay? And what I am telling you is that this term and this term will combine to give me S gen of infinity because of the properties of the Hartle-Hawking state. It is invariant. Okay, so that's how it comes. Sorry, I skipped a few steps. Okay, so you get this for a single wedge. Now you can go for a wedge V double star, which is contained. No, it's okay.
Because I haven't followed the derivation in detail. The entropy, the observer I think of as a physical state, it would be like a heavy star.
Okay.
And so, absolute values of entropy are never well defined because you're not counting the entropy of that star. That star could have a lot of entropy.
Yeah.
What I worry is that on the left hand side you have something that's a function of V star. On the right hand side you have something that's a difference between infinity and V star.
Yes, but the infinity I told you how it came from. You see that the Hartle-Hawking state. Yeah.
But between infinity and V star, it could be that this star has fallen into the black hole.
Okay.
And so the S, so that could give you a big constant.
Okay, so I don't think we are considering such possibilities, but what I would like to think about a little bit more is whether the semi-classical approximation rules that out. Okay, so the semi-classical approximation says that the quantum field operators are not strongly coupled with the observer. And if you don't have that, then you cannot do any calculation. Okay.
You have an observer which is easily detected. If I just had a two-level system, which is like thermally object.
Yeah, you could have, your picture of the observer could be a world line of someone who's just time-like world line. Yeah. Okay, so you get this monotonicity result, and you get a local GSL from this expression. So this is just basically showing how you can embed a wall-style proof, although we didn't use Raychaudhuri equation, but still embed a proof of the monotonicity of the generalized entropy in the cross-product constructions. Okay, so how much time do I have? There is small work which I want to talk about, but I can skip it. Okay, so let me just go to the final slide. So actually, let me just tell what is the issue. We just wanted to examine also the assumption of GSS that Hamiltonian generates, is a local integral on a Cauchy slice, and their assumption is it's in fact a modular Hamiltonian of some state. We just wanted to examine this for some simple cases, okay? So what is their justification? Their justification was, if H is a modular Hamiltonian, then if you add to H a piece from an algebra and a piece from the commutant, then the new sum of these three terms is also a modular Hamiltonian for some other state. So they surmise that you can use this freedom to subtract out the non-local terms from a modular Hamiltonian and make it local. So that for some state, this is a modular Hamiltonian. So what we did was we looked at this perturbatively using the path integral method for some classes of spacetimes, and we indeed found that it seems to have this structure. Okay, so I'm going to skip that, and I'm just going to come to the final slide. Okay, so the generalized second law was proven for stationary black holes by Wall under the assumption of a renormalization scheme for certain divergent quantities. The recent cross-product constructions of Chandrasekhar, Pennington, and Witten was seen as supplying such a renormalization scheme. However, a local GSL was not obtained in these constructions, and we show that using recent proposals of entropy of arbitrary subregions in Einstein gravity, it is possible to obtain a local GSL and embed a wall-style proof in these constructions. Now, I didn't talk about Kerr black holes, so I'll just end with this last comment. This works for Kerr black holes as well, okay, and works for both asymptotically flat and asymptotically ADS black holes. But in Kerr, there is an assumption about the existence of a Hadamard, which is a state which has the same short distance singular behavior as the 2-point function in Minkowski. So it's modulo an assumption about the existence of a Hadamard stationary and zero energy state on the horizon. The same thing will work for Kerr. So you have to assume this particular thing. Then what you can do is you can get the modular Hamiltonian of the Kerr spacetime, which was not known before, but this is work by Satish Chandran and collaborators, which I should have referred to. Their paper shows that if you assume all these things for Kerr, then you have a modular Hamiltonian on the horizon, a simple expression for that on the horizon. Using that, you can do the same thing for Kerr. So it works for all of them. So I think I will just stop.
I was curious, just generally, why it's called cross product?
I don't know why it's called the cross product.
Not quite the product, but you do this.
You mean this pressing?
It's not a direct product.
Yeah, it's not a direct product. You want to distinguish that.
So you have one degree of freedom which is S, which is this time.
Yeah.
You have another degree of freedom which is A, and then you look at e to the IHS times A, and then you look at some function f of S on the other side. So it's not quite direct product. Yeah,
It's a bit like the semi-direct product.
Yeah, so actually there's an alternate way of writing the cross product. You can write it as generated by the algebra's A tensor identity, where you have now expanded your space, your Hilbert space, and e to the IS modular Hamiltonian tensor e to the IS, the new operator you have added. So it's not the usual tensor product. That's
direct sum.
Yeah, so it's generated by these operators, generated by these operators.
Are there any more questions? If not, then let's thank the speaker once again.
Should we ask about the people here or no? Should we ask about the people on Zoom or not?
If they have questions, they usually.
Okay, yeah.
They say you like trading.
This is, yeah, I would be happy with this folder also.
Oh, why not?
Right, it's range.